Acids and alkalis. We've already done this. We don't need to do it again. Skip. But how do they work? Let's take a look. About a month ago when the first video came out, we talked about meta-acids, and now we're going to talk about pyroacids. So this is pyrophosphoric acid. As you can see, it's just two phosphoric acid molecules joined together. This makes it tetraprotic, i.e. it can donate 4 protons, so it's highly acidic. And there are loads of ways to manufacture it. Obviously, pyro means heat, and you can boil phosphoric acid to get pyrophosphoric acid, because it's just dehydration. You can also manufacture it with orthophosphoric acid and phosphorus oxychloride. Now, pyrophosphoric acid by itself isn't very useful, but what is useful is any salts that you can derive from it, and it's used in things like laundry detergents and water treatment, as well as a food preservative. It's also in something called ATP, which any biologists may know is how energy is stored in cells. I'm not a biology expert, so I'm not going to go into much detail about it. While we're on the topic of prefixes, orthophosphoric acid is just standard phosphoric acid. Ortho like orthodox, standard, you know. Moving on, we're going to look at something called Ka, or the dissociation constant. This is calculated by the concentration of the anion multiplied by the concentration of the conjugate base over the concentration of any whole molecules. The higher the Ka value, the stronger the acid. From that, you can calculate pKa, which is the acid dissociation constant. And this is calculated using the negative log of Ka, which we just showed how to work out last slide. Give you some quick examples. Hydrochloric acid is about -6 on the pKa scale, whereas something like acetic acid, also known as vinegar, is 4.76. The pKa scale is useful for predicting outcomes of any reactions with acids and has huge potential in biomed, as it can be used to figure out how to manufacture specific amino acids, and also can determine what behavior amino acids do, which involves things like folding. And again, I'm not a biologist, so I'm not going to go into great detail on that. And obviously you can use it for medication to find out how acidic it would be. Moving on again to our wonderful ocean, and specifically the coral. Now, carbon dioxide dissolves into the ocean, and this causes a massive problem because it creates carbonic acid, which makes the ocean ever so slightly acidic. Because of the change of environment, coral expels the bacteria that lives on it, called zooxanthellae, and so loses its colour, which is mainly why we call it coral bleaching, because it goes from vibrant colours to white. Next on my list is why oxygenated acids are normally stronger. So similar to benzene, when you add oxygen to an acid, it reduces electron density in the molecule, which leads to a more stable conjugate base. Conjugate base, by the way, I've said it a few times, it's essentially an acid but without the H+. So something like perchloric acid is much stronger than just hydrochloric acid. Next, we're looking to the stars, specifically Venus, which is a planet. Now, Venus's atmosphere, much like Earth's, is mostly carbon dioxide, but it contains traces of other things. And the most significant trace is that of sulfur dioxide. Like Earth, there's also water vapor in the atmosphere. And long story short, these react to form sulfuric acid, which creates a kind of silvery cloud cover, which is why Venus looks the way it does. But also, because Venus is so warm, about 470 degrees Celsius, it evaporates instantly. So basically what you get is an acid fog, which is a hell of a band name. It's because of this acid fog that Soviet Venera probes, which were sent to Venus, don't last very long. And because of these silvery clouds, Venus reflects almost all of its UV light, which makes it the hottest planet in the solar system, despite being the second closest to the sun. Next up, we're talking about buffers. Obviously, this is acetic acid, also called ethanoic acid, and this is its conjugate base, acetate or ethanoate. Now, a buffer will contain a weak acid, like acetic acid, and its conjugate base. They are most effective when the pH of the solution they're in is about equal to the kPa of the weak acid. Also, I said I'm not a biologist like 2 times already, but your blood makes its own buffer solution to maintain your blood pH at 7.4. It consists of carbonic acid and its conjugate base bicarbonate. When your blood gets a little bit more acidic than it should, the bicarbonate ions react with the excess H plus ions to, again, maintain your pH at 7.4. This is the Henderson-Hasselbalch equation, and it allows us to calculate the pH of the buffer solution. And obviously, as an equation, relies heavily on the ratio of the conjugate base to the concentration of the molecule. Moving on again, we're going to talk about polyprotic acids, that is, acids that can donate more than one H plus ion. Much like ionization equations, these happen in steps, and much like with ionization equations, everything happens with its own equilibrium constant. And you can work that out using this, where Ka is your equilibrium constant. What you'll find is the first constant is much bigger than the second, which is bigger than the third, etc., because it's easier to lose the first proton, and then after that it becomes more difficult. Because you're creating an H plus ion and a conjugate base, it essentially creates its own buffer solution, which makes it more difficult to lower the pH, which we discussed already. That's going to be it for today, guys. I really hope you enjoyed. I said I'm not a biologist a lot. Maybe I should be. Maybe I'll look into it. Who knows? No, I'm kidding. Of course I'm kidding. I hate biology with literally every fibre of my being. Anyway, thank you so much for showing. Remember to like and subscribe. And I'll see you next week when we'll be talking about quantum chemistry. See you then. Bye.